Okay, so this is going to be kind of a standard problem that we're going to typically have to do. And they're asking us to figure out the pH of a weak base solution. And the weak base they give us is this monstrosity right here. The good thing to note here is that it has a very small KB, which means that we're going to be able to do the 5% rule on it. But the number one thing we have to do whenever we get something like this is we need to write it in an equation, and then after that write the Ka or Kb expression. In this case, it's going to be Kb. But I don't think any of us wants to write this ever, right? Now, they tell us it's allantoin, and in reality, it's just a base. What do bases do? They grab H pluses and they pull them onto each other. So we can use that, and we can discuss and this is kind of important, is whenever we take a base or an acid and we're trying to write an equation, don't we just throw it into water and see what happens? So that's what we're going to do right now with this guy, but we're going to call this, instead of all of this, we're just going to call it all. So over here, I'm going to start off with all, and I'm going to add it to water. Now, this may seem a little bit weird to you here, just having the word all in there, but think of that just like as if it were any, this whole thing right here, the CH3, CON2, it's just all encompassed into that. This is a liquid, and it is in equilibrium. And what we do know that's going to happen here is that since this is a base, we want to pull one of the hydrogens off of this, right? And when that happens, what we're going to end up with is we're going to end up with Al grabbing, or all grabbing an H, and then that H is going to make this whole compound positive. And the H that's leaving this right here is going to leave this with an OH minus. And we one of the checks and balances we have is that we always know that whenever we have a base and we're throwing it into water, the end result is we're going to end up with an OH. If we throw an acid into water, we would have ended up with an H3O plus. So that's a kind of a check for us here. So this is our overall equation. And if we wanted to write a KB for that, we would just take our products and put them over our reactants. Kb is equal to all H plus concentration times OH minus concentration all over all concentration. And as always, a gentle reminder that we do not include H2O because it's a liquid. And over here, the coefficients in front of these were all ones. That's why we don't have any exponents up here. Well, I mean, they're ones, but something to the 1 power is just what it is. So this is the Kb we're going to be writing. So now our next step is going to be to write an ice expression or use an ice table. So we're going to go I, C, E, and we're going to take what they start us off with here. And they typically with problems like this, they will avoid starting you off with 0.80 molar. They'll start you off with a certain number of grams, or they'll start you off with a certain number of moles, and then they'll also give you like milliliters, and they're expecting to use this formula, molarity equals moles divided by volume. But in this case, we are very happy because they've given us the M. So what are we going to do? We're just going to put that into our table right here, and we're going to start off with 0.80. Now, this column right here is a nothing column. And since we start off with 0.80, we have none of this and none of this initially. And we know that our equation, therefore, our reaction is going to have to go in this direction, which means we're going to lose from this side, right? And we're going to gain on this side. And since it's a 1-to-1-to-1 relationship, whatever we lose here, we're going to gain the same amount here and here. Now, we happen to like writing whatever we lose as x, so we're going to write minus x here. And since it's a 1-to-1 ratio, we're going to write plus x here and plus x here. And then at equilibrium, we're going to go 0.80 minus x, and over here we're going to go x and x because, again, we had zeros to begin with. Now, through the magic of me having an iPad here, I'm just going to grab this and bring it down here so we know this is what we're going to plug things into. But if we take a look at our expression, it's going to appear, since it's a 1-to-1-to-1 ratio, we're going to end up with a dead frog. And again, for those of you that are unfamiliar with that, we just plug our variables back into our equation. So we're going to take these variables right here, and we're going to plug them into here. And then we're going to take this variable right here, we're going to plug it down into here. Now, they've given us the KB, that is this right here. And what we need to be aware of here, when they ask us to solve for the pH, that's the negative log of the H plus. But when we're dealing with a base, what we're actually solving for when we solve for X is OH minus. So when we finally get our X value from this, we're going to know what our OH minus concentration is, and then we're going to have to switch that over to H plus to figure out our pH, which is what they're asking for. So let's just plug all the numbers in, the variables in we've gotten, and it's going to be X times X on the top, all over 0.80 minus X, and that's going to be equal to 9.12 times 10 to the negative 6, which, as we know, is a really, really small number. And because this is such a small number, we feel really, really free to use what we call the 5% rule. Now, I call it the 5% rule, but sometimes they call it the weak acid or weak base approximation, which means that this we can assume is going to be so tiny compared to this, because remember, this is the amount that's dissociating or leaving from 0.80. And if the ratio of our products to our reactants is 9.12 times 10 to the negative 6, we're talking about 100,000 times less is going to form over here. So what we're going to do is we're just going to write 5% rule like this to get rid of it. Now that we've done that, now we're in mathing world. So you can gather your terms if you'd like. X squared is going to be equal to 9.12 times 10 to the negative 6. And that's all going to be multiplied by our 0.80, which by getting rid of this this x right here, we avoided having to use a complex polynomial or do a quadratic equation. Now, through the magic of having done this already, I can square both sides and I end up with an x value equal to 0.002701. Now, it is really important in all these problems that when we define what our X is equal to, we need to also say that it's equal to our OH minus concentration. Now, we know this because up here, when we look at our problem, this right here, this is our OH minus. Now, it also is our base concentration as well, but we don't really care about that. They didn't ask us for that. But if they did ask us for that, we could write our ALL, and by base I mean acid, because this is clearly an acid. So we have this right now. So our next steps are, can we switch this over to get to pH? And by the way, just as a small check, if you were to take this and divide it by 0.80, the number you're going to get here is going to be less than 5%. Another way of doing that is if you were to take your 0.80 and you were to subtract 0.002701, would that change this 0.80 in any way? And the reality is that no, it wouldn't, because this part of the number right here is actually smaller than the 0.80. So now let's do it. We can do it one of two ways. The normal way of doing this is, well, actually, there's no normal way. You can do it more than one way. Is H plus times OH minus is equal to 1.0 times 10 to the negative 14. And then we can just take this value right here and we can plug it into right here. So when we do that, we can rearrange this. In other words, what I'm going to do right now is I'm going to take this and bring it down below here. So I'm going to take this and divide it by my OH minus concentration. It's kind of a messy thing here, but I don't want to have to rewrite the whole thing from scratch. I'm going to write H plus, and by the way, that's also equal to H3O plus, but 1.0 times 10 to the negative 14, and we're going to divide that by 0.02701. And it's okay to keep extra significant figures right here and just do our sig figs at the very end of the problem. In fact, that's the way we typically encourage you to do it. And when we solve for our H plus concentration, we're going to realize that it is equal to 3.739 times 10 to the negative 12. Again, this was all done off screen, and this is the molarity of it. Now, they didn't ask us to solve for the H plus concentration. And by the way, H plus is the same thing as H3O plus. So don't ever for a second feel like if they write this equation like this, OH and H3O plus, if they have these two multiplied by each other, they are the same exact things as each other. So then we're going to take the pH, which is the same thing as saying the negative log of this number right here, 3.739 times, oh, that's an ugly times 10 to the negative 12. And when we do that, we're going to end up with 11.4272. Now, typically what we do in a problem like this is we look back up at our original problem. We'd see that they gave us 2 significant figures here and they gave us 3 significant figures here, so we'd use 2 in our answer. But ALEKS wants you to do it to just 1 decimal place. So even though we know that in reality we should cut off right here and give 2 significant figures, remember, whenever we're dealing with pH, we ignore the numbers before the decimal and we count after the decimal. So when we do that, we would have gone 11.42, and then this 7 would have rounded this up. But they only want to have 1 significant figure in the problem, and because of that, and because we're bowing to the overlords at ALEKS, we're going to write 11.4. Hopefully this has been helpful to you.